Section 2.5, we're going to write and solve compound inequalities. So our last section, we just solved inequalities. Now we're going to put two inequality statements together, okay? And that is what a compound statement is. Here we have a compound statement. Basically, a compound statement is a statement made out of connecting two statements. So basically, we take two statements and we connect them with the word and or and an or. So we connect them with either the word and or is a compound statement. So it's two statements we put together with and or between them. Okay, so let's go ahead and let's look at statements and let's work at connecting them. So here, for task 1, stay A, Mary is a 9th grader. She plays softball. So now we can either connect these two statements with the word and or the word or. Okay, so if we look at using the word and in between them, okay, we always often when it comes to compound statements, we talk about its truth value. Is it true or is it not? So when we're talking about a truth value, we're asking ourselves, is it true or false? So truth value, is it true or false? And how we use the word or there is it has to be one or the other. In normal everyday language, when we use the word or, when I say you can have a cookie or a cupcake, it usually means you can only pick one. In mathematics and logic, or is used differently. Okay, so we're going to look at that today, how we use or differently in mathematics and logical thinking. Okay, so here, if I use and in between, Mary is a 9th grader and she plays softball. This statement with an and could be true if both are true. Meaning, yes, she must be a 9th grader and she must play softball. She has to do both. Now, with an or statement, it still can be true if both are true, but or only one needs to be true. But they both can be. Okay, in that last bit, they both can be true. Let's use yellow instead. That'll make it easier. They both can be true is how or in mathematics and logic is different from or in everyday language. Okay. All right. So here I could use an and or I could use an or, but in this case, an and would probably be a better use if they were both true. Okay. So if Mary is a 9th grader and she plays softball, if she's a 9th grader, if she's a 9th grade softball player, then and would be a better fit there. Okay. The next one, Francis walked to school and he rode the bus to school today. So now we have to ask ourselves, does an and or an or make more sense? Now, and again, both must be true. Is it possible for Francis to both walk to school and ride the bus to school? Nope. In this case, an and would produce a false statement. So in this case, or would be a better fit. Francis walked to school today or he rode the bus to school today. If he has both for options, or is a better fit. Okay. Animal X is a cat. Animal X is a bird. Now let's look. And or. Which one's a better fit? Okay, for and, again, both must be true for and. Both must be true. Now we have to ask ourselves, are there any animals that can be both a cat and a bird? No, those are two distinct, I believe, phylums, kingdoms. I don't know. Scientific classification is not my strong suit. But I know they're two different things. So you can't be both a cat and a bird. So or would make a better sense. It could be a cat or it could be a bird. It's either one or the other or both. Again, for or, it's one or the other or both. In this case, or both won't work. So one or the other. Okay. The next one, 5.2 is an integer. And, oh, I can't spell and all of a sudden. 2.5 is a whole number. Again, for and, both must be true. Is 5.2 an integer? If we remember what the integers are whole numbers and their opposites. Well, I can tell right there 5.2 is not a whole number. It's an in-between. It's in between. 5.2 on a number line is in between 5 and 6. So it is not an integer. So no, that's not true at all. So I know for sure I can't use and. Even if the second statement is, I can't use and, because for and, both must be true. For and, both must be true. Okay. All right, 2.5 is a whole number. Well, along the same lines as the last one, 2.5 is in between the whole numbers 2 and 3. So no, it's not a whole number. So or wouldn't work either. Okay, so this statement, whether and or, would be false. Okay. Okay. So now we're going to look at the graph of some compound inequalities. Again, we're putting inequalities together using the word and the word or. Okay, so here we're connecting vocabulary a little bit. In chemistry, a compound is a substance formed when two or more elements are combined. A compound inequality is made up of two inequalities combined into one statement by the word and or. At first glance, so if I look at this one, this looks kind of crazy. It's got two inequality symbols, but no and no or. Okay, this is a shorthand way of writing an and statement. What this means is -3 is less than or equal to x, and x is less than or equal to 3. We only use this notation to put together an and statement. And if you notice, the inequalities always go the same direction. Okay, what I mean by that, both of these, this guy and this guy, are less than signs. You will never write a compound inequality like this. The first one is a greater than, the second one is a less than. You never write them that way. Okay? They always go the same direction when we're putting them together to make that and statement. Okay? So really what I have in this statement is, if I rewrite this going the other way, x is greater than or equal to -3. I just flipped it over. So I know x has to be greater than or equal to -3. So I'm going to go ahead. There's my 0. There's -3. And then I'm also going to need a +3 for this guy here. I know to graph this guy, x has to be greater than or equal to -3. So I'm going to do this above. So greater than or equal to is a closed dot. Greater than, it needs to go this way. Okay. Now for this guy, I know x has to be less than or equal to 3. So we go from here down this way for forever. But it is a and statement. Both must be true. So for them both to be true, on my final graph, I'm only going to shade where it's both shaded on the blue and both shaded on the green. So it would just be from -3 all the way up here to 3. Close dot. I can't include the points up here because they're not covered under the green. The green doesn't consider those. I can't include the points down here because they're not in the blue. Okay. So for an and statement, we shortcut it by putting it together. And it just means and. So our first step a lot of times in analyzing these is to break them up. Okay, so for this next one, again, this is an and. -1 is less than x, and x is less than 2. So if we flip this guy around, x is greater than -1. So if I'm graphing this, here's 0. So to graph this guy, x has to be greater than -1. So from -1, oh, I need an open dot. It's not equal to. From -1 on up. Okay. And now for this one, I need less than 2. So there's 2. So again, from 2 on down. And since it's an and, I need to shade where both are true. So it'd be from -1 to 2, shaded in between. Okay. And you can tell here, if I just read this original, if it's listed from least, we normally like to list them least to greatest. For example, if you notice -1 is smaller than 2, it's least to greatest as we read it from left to right, which means then that we would use less than symbols. You can rewrite this using it the other way around, 2 greater than x greater than -1. But just in general, we tend to, because our number line goes least to greatest from left to right. So we like to write these least to greatest left to right. And you can tell here that x is between -1 and 2. Here, we shaded all the numbers in between -1 and 2 with a less than, open dot at -1, less than, open dot at 2. Okay, so often, once you get pretty good at these, you can go from here to here without having to write all these middle steps. Okay, and that's okay if you can do that consistently and get them accurate. Okay, all right, now we step it up a notch. We don't just have an x. We've got an x times 4 minus 2. Okay, very similar to how we did the last ones. Again, this is a double inequality. I've got an inequality here and an inequality here. They're going the same directions. They're both less than. So first step, I'm going to break this up into an and. We have -6 is less than or equal to 4x minus 2. So this whole thing is in the middle. So that whole thing goes here. And now 4x minus 2 is less than 10. Again, there's my middle. So always identify where your middle of these inequalities are, and that's the point that repeats. Okay, so now we're just going to solve each of these separately and then put them together. So if I solve this left side, I'm going to start by adding 2 to both sides. My goal, get that x guy by itself. So I add 2 to both sides. -6 plus 2 is -4. Is less than or equal to -2x plus 2. Sorry, -2 plus 2 is 0. Left with 4x. Divide both sides by the 4. I'm dividing by a positive, so I don't need to worry about my inequality. -1 is less than or equal to x. Or if I flip it over, x is greater than or equal to -1. Okay. All right, so it also does say to graph it. So I'm going to go ahead and I'm going to graph this, but it's an and statement, so I'm just going to mark my 0, mark my -1, and I'm going to do it above. So x is greater than or equal to -1 is that guy right there. Okay, now let's solve the other half. So again, I add 2 to both sides. So I get 4x, -2 plus 2 is 0, 10 plus 2 is 12, divide both sides by 4, x is less than 3. So let's put that on my graph. X is less than 3. 1, 2, there's 3. So less than, open dot, go this way, less than 3. So now my final shading, since it is a and statement, both must be true. So I'm looking for where both are shaded. It would be in between -1 and 3. Okay. All right. Now, I'm going to show you a different way of solving the same problem. If you notice, our work looked a lot the same. What do we do? In this first step here, we added 2 to both sides over here. We added 2 to both sides over here. And then in our next step here, what do? Divide by 4, divide by 4. Oh, look over here. We divided by 4. You can actually do it kind of all in one step and solve it all basically as a 3-sided inequality. So I'm not going to split it up. I'm going to solve it just like this, but again, my goal is to get this x term by itself. So I look to see what's happening to x in here. Okay, so in here, what's happening to x? I'm taking 4 times x and then subtracting 2. So I have to undo the subtract 2, so I'm going to add 2 to, instead of both sides, all 3 sides. You have to do it to all three pieces if you're going to leave it together like this. So if I add 2 to all three pieces, negative 6 plus 2 is negative 4, less than or equal to, negative 2 plus 2 is 0, so 4x, 10 plus 2 is 12. Okay. Again, I want to get this x term in the middle by itself. So I'm going to need to, right now it's multiplied by 4, so I have to divide by 4. Again, all three terms. Negative 4 divided by 4 is negative 1. 4 divided by 4 is 1. 12 divided by 4 is 3. So there I can tell from my answer, again, double check my inequalities. Oh, wrong one, not this one. My inequalities are going the same way. They're both less than. We're going least, it goes least to greatest. So I can tell then my x, if I go to graph this, my x has to be in between negative 1 and 3. It can equal negative 1 because of that equal sign. So we would have a solid dot here. It can't equal 3 because that's a strictly less than sign. So open dot there. I got the same graph. Solved it as a three-sided equation. Basically, it's got three sides. The ones that are written all as one inequality, like this guy here, you can do that with. This next one, solve x minus 2 is greater than negative 1, and it's got the word and in it. You can't solve this one inequality. You just solve each one separately. So first, let's go ahead. Let's solve this left side. X minus 2 is greater than negative 1. So right now I'm subtracting 2, so I'm going to add 2 to both sides. Negative 2 plus 2 is 0, so x is greater than negative 1 plus 2 is 1. So if I go to graph this, x has to be greater than, here's 0, here's 1. X has to be greater than 1. So open dot greater than 1. Okay. All right, and then we do the next side. 4x is less than or equal to negative 8. Divide both sides by 4. X is less than or equal to negative 2. Okay. X is less than or equal to, all right, negative 2 is right there. Less than or equal to, okay. Again, remember this is a and statement. Both must be true. Both must be true. Well, are there any numbers that are going to be shaded up here in green and shaded down here in red? Do they overlap at all? Nope, which tells me that there are no numbers that will make them both true. So this compound inequality has no solution. There is no solution. There is no number that will make them both true. That I can plug into this side and be greater than negative 1 and plug in this side and be less than or equal to negative 8. So this one has no solution. So the graph of this is just a straight line, nothing shaded. There's 0. There's a graph. There's nothing shaded because there's no way that they're both true. Okay, so there we've covered and. Again, and both must be true, so you only shade the parts that overlap. Whereas or, it consists of points that appear on either graph of the simple inequalities. Okay, so here it doesn't need to be on both. It needs to be on either one. Okay, so when I'm graphing here I have an or statement. X has to be less than negative 2.5. So here's 0. Okay, there's negative 1, negative 2, negative 3. So negative 2.5 is going to be here in the middle. Open dot. Less than negative 2.5. So shaded this direction. Okay, or x has to be greater than 0. So greater than or equal to 0, 0. Shaded this direction. This is very similar to our last problem. They go opposite directions and they never overlap, but it's an or. Either can be true. So my final graph on this is strictly going to be just these points on down and these points, including 0 on up. The graph is actually both. So I can pick any number from 0 on up and it will work in this compound inequality because it'll make this guy true. I can pick any number from negative 2.5 on down because I can put it in this half and it'll be true. The only numbers that won't work are these numbers in between because they don't make either of them true. Okay, so you're looking for basically what either one. Okay, so let's go ahead and solve. You can't solve these compound inequalities all together with an or like you can an and. Like this guy, remember where we solved it all as a three-sided? Or can't be written as a three-sided because it's a strictly or. So you're going to have to do it in two halves. So let's go ahead and let's solve this half. I'm going to write as plus a negative 8. So I'm going to add a positive 8 to both sides. 3x is less than or equal to negative 14 plus 8, negative 6. Divide both sides by 3. X has to be less than or equal to negative 2. Okay. So if we go ahead and graph this, x has to be less than or equal to negative 2. So less than or from here on down. All right, now let's graph the other half. 5x plus 7 is greater than 17. So I'm going to add a negative 7 to both sides. So 5x, negative 7, is greater than 10. Divide both sides by 5. X is greater than 2. So here's 2, shaded this way. So for my combined graph, since this is an or, either can be true. We just graph both pieces. So from here on down, and then from here on up. Okay, if you notice, this is how I expect your work to look. I draw my in-between graph above, and then I apply my or and put it together. Just like how we did up here, how I drew my two graphs above, and then I put it together on the number line. That's what I expect your work to look like. Okay, so how I do my work is how I expect your work to look. So somebody else can follow what you did. Okay, because sometimes you'll see in the next one, it isn't always opposite directions. Like it doesn't always work out like this with an or statement. Just like it doesn't always work out with the overlapping with an and statement. These didn't overlap. Okay, so here, this next one. So again, we're going to do the two halves. This first half, 3x plus 6. I'm going to add a negative 6 to both sides. So 3x is greater than negative 3, divide by 3. X has to be greater than negative 1. Okay, we go to graph this guy. Here's 0, negative 1, greater than negative 1. Open dot going this way. All right, other half. Negative 2x plus 5 is greater than 5. I'm going to add a negative 5 to both sides. Oh, missed my x. Negative 2x is greater than 0. Negative 5 plus 5. Divide both sides by negative 2. Oh, careful. Star there. I'm dividing by a negative. My inequality has to flip. So now my x has to be less than 0. Okay, so from 0 on down. Okay. Now I need or. So either or could be true. Or both. For or, it's either either or both. Okay, so it could be an overlap, it could not. So if you notice on this one, this actually covers the entire number line. Because if I pick a number up here in blue, it'll work for this blue bit. If I pick a number down here in red, it'll cover this red bit. But between the blue and the red bits, it actually covers the whole entire number line. So my solution set, my combined, since this is an or, I shade the whole entire number line. And how we write our answer to this, I would not write these two pieces. Because when I put those two pieces together, I actually get every single number. And how we write that is we say it's all numbers or all the real ones. It's all real numbers. That is my solution set. Basically what that means is it doesn't matter what number I pick, it will work because it will make at least one of these guys true, if not both of them true, no matter what number I pick. If I pick 10 up here, it'll work because it'll make the blue guy true. If I pick negative 100 down here, it'll work. It'll make the red guy true. If I pick negative 1.5, it'll work because it actually makes them both true. Okay, so any number will work. So my solution there is all real numbers. Okay. Now let's look at a way in which these compound inequalities are used in a day-to-day. So here we have a manufacturer make single-serve packages of oatmeal, so like those little packets of oatmeal for breakfast used. For quality control, there's an acceptable range of weight for each package, okay? So like each package has a certain amount of oatmeal in it, and it can't be more or less. So meaning for them to know their machines are working how they should work, is they measure how much oatmeal actually ends up in each packet, and they have an acceptable range for that weight. Meaning, okay, if it's above by this little bit, it's okay. If it's below by this little bit, it's okay. Because again, not each will be exactly the same, depending on how precise you measure. The acceptable weight range for each package should be within why is that not working? Oh, sorry. Within 0.25 ounces of the ideal weight. So write and graph a compound inequality to represent the situation. What is the weight range the manufacturer will accept for the package? If you notice over here in the picture, they say over here, the ideal weight of an oatmeal package is 1.5 ounces. So basically, I need to be between. So I'm going to start again by writing a verbal model. I talk about this all the time. I'm still waiting for you guys to write them. Whenever you're dealing with a word problem, kind of write a bit of a verbal model first. So the actual weight of the package needs to be between actual weight needs to be between 0.025 ounces of ideal weight. Okay. So basically the actual weight, okay, could be, if it's too heavy, it would be 0.025 above. So the actual weight could be 0.025 more than ideal. Okay, so the actual weight could be between that or 0.025 less than ideal. Okay, so the actual weight W, so for between, this would be, if it's less than ideal, okay, this is going to be smaller than the actual weight. So this would be a less than, or it could be equal to. It could be to exactly that. And this one would actually be more than the actual weight. So it would be a less than or equal to. So my actual weight W needs to be 0.025 less than ideal. Well, we know the ideal weight is 1.58. So it could be 1.58 minus 0.025, less than that. So too small. Or it could be more than that, the 1.58 plus 0.025. And if you get the subtraction problem backwards, you'll find out it won't work. You'll get a negative. The weight can't be negative. So I need to take 1.58 and subtract 0.025. So we go, oh, let me get out of there. So I'm going to take 1.58 and subtract 0.025. So between 1.555 and 1.58 plus 0.025, 1.605. So as long as the weight falls in between these two values, 1.555 and 1.605, okay, so I'm just going to, okay, I could do all the extra marks in between. I'm just going to go ahead and just mark those two on my graph. It needs to fall in between those two amounts. Okay. So here's the question. So would a 1.63 ounce package be okay? Would that be okay? 1.63 is larger than 1.605. 1.63 would be up here because this is 1.60. So 1.63 would be too big. So nope, it would not be okay. It would be rejected. We would not send it out to stores because that one would be over. The package would be too big. So nope, a 1.63 would not.